matrix, and then you can take DAGs of each one.
Right.
Thank you. Yeah, I think that's pretty much all I'll need on that. Is there anywhere in the, I haven't looked at this chapter of the textbook. Do you know if it goes over this in the textbook? Or?
Maybe not in much. So maybe they don't go much into technicalities of calculation. That will discuss the general ideas.
I see.
So that's why we have this homework. Okay, where do you want to go?
Professor, we could actually calculate the AB minus BA. Then at the end, we can just get the complex conjugate, right?
The Hermitian, yes.
Yes. Okay.
Yeah, that's what I was trying to say. Yes.
Thanks.
You had mentioned the other day that you wanted to go through number 2, the proving the quality.
If you feel comfortable with it, we don't need to. But I was thinking that maybe that's the most difficult problem in the homework. But that's your call.
I would like to go over.
Yeah, I wouldn't mind going over number 2.
Okay. So what are you tempted to do? How would you get started? Maybe that's my question. So we are given a suggestion, right? When you are given a suggestion, to be honest, I don't know if the suggestion is the only. I'm sure it's not the only way to demonstrate this inequality. But since we are given a suggestion, I think it's smart to follow the suggestion.
So you could multiply that binomial through and then take the derivative with respect to lambda and set that equal to 0, right?
Yeah, that's what I would. Yeah, that's my temptation too. So let's do that. So I'm gonna just write this. Oops. I'm gonna write this, but expanding, right? So we have alpha.
Could you share your screen?
I'm not sharing my screen now.
No.
Ooh, okay, sorry. I was starting to write stuff. Start. Thank you. Right. So yeah. So I was saying let's follow the suggestion, and to do that we start from this inequality that is given to us, and we expand it. And also by expanding it, we are going to see that that equality is valid. So I have alpha. I have maybe lambda square, beta. And then I have lambda alpha beta plus lambda star, sorry, beta alpha. And that's greater than 0. Then how? So one of you. I'm sorry. It's going to be impossible for me to learn your names. But one of you was suggesting to differentiate with respect to lambda. How do you do that?
So in here, we're not assuming alpha and beta are orthogonal, right? So that those ones don't disappear.
Oh yeah, they're not. Yes.
Okay.
Yes, because you see that otherwise the equality that we would have to demonstrate would be kind of trivial, right?
Gotcha, right.
So you see that this is exactly the same. That's an inequality that you're familiar with, right? If you have two vectors, u and v, the dot product uv is equal to maybe I should put is equal to the product of the magnitudes, right? Multiplied by the cosine of the angle between the two vectors. Right? And so you see that here, this is the square of the inner product. So if I were to square the equation that I wrote, I would magnitude square so that I drop any possible sign. And then this would be, this would be squared, and this would be squared, and this would be squared. And so you see that as a consequence, the product of the squared magnitude of u with the squared magnitude of v is greater than the magnitude square of the dot product of the two vectors, because this number is always smaller than 1. You're good with that?
Yep.
Okay, so then we need to figure out what is the value of lambda that, since that's the suggestion, that makes the left hand side as small as possible.
So I mean, differentiating with respect to the first 3 terms seems a bit reasonable. I'm just not 100% sure how to differentiate with respect to lambda star.
So yeah, so because lambda is a complex number, right? And there are ways to take derivatives with respect to complex numbers. I find that a bit scary. So what I would do, I would rewrite lambda in a different form. And so maybe there are several ways to do that, but when I wrote the solution, I don't think that I had done that problem before this homework. When I wrote the solution for myself, what I did is the following. I said, okay, let's consider that lambda is some number rho that multiplies exponential I phi, where I have rho that is real and rho that is positive, and phi is just real. And so the best lambda is going to be the lambda that has the rho that minimizes the expression with the phi that minimizes the expression as well. So it's a matter of taking essentially rewriting this expression, substituting lambda for this expression that I just wrote, and then take the derivative with respect to phi, for example, first, and then with respect to rho, and have that equal to 0. You want to do it, or?
Yes.
Before we continue, why did we start with this first expression where it says, for this, consider that one expression? Like, where does that come from? Why do we start with that expression?
That's how the problem was written. I did not think much about it.
Like, if we were
you see that if I were to call this psi,
yeah,
this would this would exactly be psi de Bra. And so it's clear that since this is an inner product of psi with itself, it's clear that it is equal greater than 0.
Yeah.
Right. So that's it.
Oh, okay. So it's just kind of like an expansion.
So we know you know that this is always true.
Right.
And I guess that if you wanted to show this, one way to proceed would be to start from this with the vision that psi written in this way leads you to demonstrating this by figuring out the value of lambda that makes this expression the smallest.
Okay. Okay. Thank you.
So I'm not claiming that I would be smart enough to if I were given the task to demonstrate.
Yeah.
If I were given the task to demonstrate this, I'm not sure that I would right away think about defining that. But that's the way that is suggested in the problem. So I'm just obedient and I stick with it. In fact, that's the type of those of you who are in math, maybe they can say something about this. But I find this type of demonstrations difficult to deal with because the statement that we have to demonstrate looks obvious. And often I find it makes demonstrations more difficult to see through when the result that you're trying to demonstrate is that clear, right?
Uh-huh. Okay, that answers my question. Thank you.
Okay. So let's carry on with it. So we have, oops, I need to take a pen. So I have still alpha. I need to remove my glasses. I have alpha plus magnitude of lambda square. What is that going to be?
Rho squared.
Just rho square. Beta plus rho exponential alpha phi alpha beta plus rho. So maybe I can write that since I'm going to have rho twice. Exponential minus I phi beta alpha, and this is greater than 0. Okay, and so maybe we should give a name to that thing. I don't know, I can call that P maybe. And so at this point, what we can do, we can calculate the derivative of P with respect to phi. So if we do this, the first two terms drop out, and then we have I rho times exponential I phi minus and we would like to set this to 0. Right, so that means that the two terms that are between in the bracket, they are equal to each other, and so that means that exponential of I 2 phi, 2 I phi, right here, 2 I phi is equal to beta alpha divided by alpha beta. Oops, am I doing something wrong here? I'm checking the solution that I wrote earlier. Oh. What did I do here? I'm sorry. And so then what the next thing that I did, I multiplied by beta alpha over beta alpha, which is fine because I'm just multiplying by 1. And then I have so this is beta alpha squared divided by the magnitude of alpha beta. Sorry. Magnitude squared. And then if I take the square root, that gives me that exponential of I phi is equal to beta alpha divided by magnitude. Okay, so that's phi. And then we can replace phi exponential I phi by this expression, and take the derivative with respect to rho. So if I do that, everybody's happy with that?
Yeah.
Yeah, able to follow, yeah.
So we have alpha plus rho square beta, and then I have plus rho, and then I have beta. Maybe I can just copy because I'm lazy. Alpha times alpha beta and then I have minus the complex conjugate of exponential I phi. So that's the complex conjugate of this thing. So this is a real number. So just complex conjugating this is just flipping the bra and the cat, right? So that's going to be alpha beta divided by the magnitude of alpha beta multiplied by beta alpha. I can close the bracket. So that's P with that value of phi that we found. And then we can take the derivative of P with respect to rho. And so it's going to give us 2 rho beta plus that thing. Maybe I can just copy that. Paste. Equals 0. I have the impression we can simplify this thing, yeah, because you see that this is just the magnitude square of alpha beta. And this is the magnitude square of alpha beta. So that would be equal. So maybe I made a mistake somewhere. Can you help me? Did I mess up something?
Should that be plus alpha beta cat? Because you just plug in, switch the alpha and beta, and it doesn't change the minus, right?
Show me on the screen. I'm not sure.
So it's just like you put back the e to the power of I phi in the p. So then that part in the bracket, the last bracket, it should be plus, I think.
Here? So here?
Yeah, I think that part should be plus.
Why should we be plus?
See,
oh yeah, because we had a plus initially.
Yeah.
Yeah. So that's my mistake. You're right. Exactly. That's exactly what I was doing. Thank you. I was not seeing that. I think I here as well. Yeah. Yes. So this is going to be like maybe in fact it would have been cleaner if I had manipulated this already here before taking the derivative or anything. But so this is this ends up being 2 rho beta plus 2 times the magnitude of alpha beta equals 0. So we end up with rho equals of the magnitude of alpha beta divided by beta. So these are the values of rho and phi for which P is stationary at least. And then it's just a matter of replacing, right? So I'm going to replace this in here.
Should rho be negative?
I think that
should rho be negative?
Yeah, should it have a negative sign out front?
Yeah, you're right. But then that's weird because this is a positive number. This is a positive number. You see that that would make rho, a number that I chose positive, be negative.
So did a negative get dropped somewhere?
Yeah, I'm not sure. So I'm eyeing at the same time. I'm eyeing on my solution, and when I wrote my solution, I did not notice that. But that's bothering me now because I think rho should be positive.
So I actually have a question about when you plug in EDI phi. So it's the third line from the bottom.
Oh, yeah. Sorry, yeah.
Yeah, the third line from the bottom. Why is the the denominator of when you plug in E, why is it the same? Why don't you flip the bras and kets on the denominator as well as the yeah. So when you plug in E, so
because
in parentheses,
like here, you mean here and here?
Yeah. So why isn't that flipped as well? Is that not is it the same number, magnitude of it?
Yeah. So this is also equal to beta alpha, right?
Okay.
So you see, you remember that this is the complex conjugate of that. Sorry,
Right.
this is the complex conjugate of that. So when you take the magnitude,
It's the same.
you get the same
That
thing.
makes sense. Right? Yeah.
Okay. So now I am realizing that maybe my mistake is with phi. You see what we wrote? We wrote this, and I'm happy with that. And then we said take the square root. But I think the square root that gives us exponential I phi is plus or minus that. And that plus or minus essentially, that's still rho is positive. I'm bothered by that. Okay, I did not think about that earlier.
Yeah, how exponential of something can become negative.
Okay, so clearly we have a question about that. I'm not sure about the answer. Maybe I can write sign. But let's carry on and see what happens. And maybe in the meantime we will have an idea about why we have this weird sign issue, which I honestly am not seeing through at the moment. But let's replace P in P. Let's replace rho by what we found. So we have P that is still alpha plus rho square. So whether there is a minus sign or not gives us, I need to zoom in, I'm sorry. Alpha, alpha beta squared divided by beta squared, and this is multiplied by alpha beta plus no, what am I doing here? Sorry, let me erase that. I'm writing rho. No, I don't know. I keep confusing myself. Sorry. So I have alpha beta magnitude square, right, for this term here, divided by beta squared. But you see that it is also multiplied by beta. So I only have one beta square in the denominator. Then I have plus. So then I would have minus. Let's see what happens with this minus sign. Maybe I can circle it with red, since we have this doubt about it. And I can just write this here. And this, we said, is just the magnitude of alpha beta, right? So I have magnitude of alpha beta. Oops, that's right. This is to be positive. There's something going on there. So clearly, if we multiply, so beta beta is a positive number. So if I multiply by beta beta, I'm doing something. I'm doing something wrong somewhere. I cannot. If I but let me move on. If I multiply by beta beta, that's not p anymore, but I have alpha alpha beta beta. And my problem now is that you see I have almost what I want, right? Because I have this alpha beta square, right? Which we want to have. But the problem, of course, is that I have this minus that, which amounts to 0. So I'm doing something wrong somewhere. Have I dropped something? Or... Is there anyone who sees where I'm making a mistake?
I'm trying to figure it out too, but I haven't seen anything yet.
I'm just blind at the moment. Yes. Okay, my mistake is that 1 plus 1 is 2, right? So, okay, sorry, I'm seeing I apologize. So we have alpha, okay? We have rho square beta beta. Then we have rho, which I wrote here, that multiplies all that stuff, okay? And then my mistake was to say, okay, so this is the magnitude square of alpha beta divided by the magnitude of alpha beta. And that's what I wrote here. But the thing is that I have 2 of them. Right? So I'm missing a 2 here. You see that?
Mm-hmm.
Yeah, that makes sense.
So that's the thing. Somehow I dropped that the fact that there were 2 of them instead of 1.
I had a question regarding this step because my from just looking at it without thinking about it any further, I guess my question would be like, can you, if you have like the magnitude of like, let's say alpha beta, you can't just like, if you're multiplying it by another like fraction with the magnitude of alpha beta, they don't just cancel, right?
You're questioning that?
Yeah, but I think I just answered my own question because I realized I have to do the operations within the parentheses first before you do anything with a row value. So.
Oh, right, yeah. So, but the idea here is that this is you see that this is a complex number that multiplies the complex conjugate of the same number. So this is the magnitude squared divided by the magnitude of the same number. So that's the magnitude of that complex number. And then we have the same thing here again. So we have 2 of them.
Okay, yeah, that makes sense.
Right? So we end up with this. Paste. And that's greater than 0, which is exactly what we squared, which is exactly what we were asked to find. So that works out. there is one point of discomfort associated with the minus sign on the row, which is necessary, right? Because if we did not have that minus sign, then what would happen? This would be a plus sign, and 1 plus 2 would be 3. So that minus sign needs to be there. I'm just bothered by the fact that it seems inconsistent with this writing of lambda. What about the math majors helping us with complex variables? Why do we end up in this situation? I don't think it's a mistake. I'm thinking we're thinking something wrong. But no one has an idea?
I mean, we technically didn't really use the assumption that rho is positive, right? So, like, I mean, we just kind of had it in the back of our mind, but
that's true. And whether you flip the sign of rho or flip phi by pi, you get the same complex number. So it doesn't sound horrible. Just okay, maybe it's not important, but I am puzzled as to why we are forced into having a negative rho. There is nothing wrong with it, but so maybe the one thing that I should not write is that I can always say that any complex number can be written in that form, but in fact any complex numbers, if you consider rho being either positive or negative, every complex number has 2 ways of being written this way. And it seems that the work that we did is selecting just one of the way, which is the way where rho is negative, which I find funny. Maybe that's in the, okay, I will need to think about that. I'm a bit puzzled by, maybe that's in the taking of the square root that I'm thinking something wrong. Okay, if you show that, I'm happy with it. If I think something about this, I will get back to you. At the moment, I don't see it. Any question on this? If not, we can move to any other question you may have about the homework.
So I guess I do have a question. So just showing, showing that confirms the Schwarz inequality. It still looks different, but like, I guess you said showing that will be sufficient. Like, I feel like there could still be other steps that you could take, but you mentioned that.
No, so, this inequality, oops. So this inequality is exactly this one, right?
Yeah. Yeah, that is, yeah, okay.
So that we see that we have this minus sign right here. So
okay, yeah, I can convince myself that that's the case.
So we have that. So that's exactly the inequality that we were supposed to demonstrate. And I think that the important part is to remember that inequality, which is just stating that the product of the square magnitudes is always larger than the square of the inner product. Which when you play with usual vectors in 3 space, for example, is absolutely obvious. That's what I try to illustrate up here.
Okay, thank you. I see that now.
Okay. So just this. So while here it is kind of obvious when we are dealing with 3 space real vectors. This result is just much more general, right? Because there is no limitation on the number of dimensions of the space in which these vectors are, and additionally, it's a complex vectorial space. So it's a the name of it is a Hilbert space. Okay, where do you want to go? I was thinking that maybe another difficulty that you could encounter with this homework is with the traces. Have you done the problems with the traces?
Yeah, I've never heard of a tracer before, so that'd be nice.
But you have the demonstrate. You have the not demonstrate. You have the definition here, right? The trace of A is the sum of its matrix representation diagonal elements. And if you are working in a given basis UI, then that amounts to summing up. So it's sum over I of all the diagonal elements of the matrix that is representing the operator A in this basis. Now you see that the way it is worded suggests that trace of A is a property of A, and I have been trying to highlight the fact that an operator is something that exists independently from the choice of a basis, right? So that means that this calculation is going to should give a result that is not dependent on the choice of the basis. Because if the result of this depended on the choice of the basis, then this number would not be a property of A. It would be a property of A in that basis, right? But what I'm saying clear?
Yeah, I'm following.
Yeah.
Okay. So the idea is to show that if we add another basis, then we would find the same result. So how would you do that? How would you start?
I would try throwing in the identity operator somewhere.
Yes, that's a good reflex. And how would you write the identity operator?
Well, so we need a different basis to write it in.
Yes. So let's give it you're exactly the right strategy. So let's say we have another basis that we are going to call. So this I have a hard time writing very small on the tablet, so I need to zoom in. So we can call this new basis V sub I. Okay. And since it is a basis, we know that the sum over I of the V sub I, the ket times V sub I, the bra is equal to the identity. So then maybe we can start from the expression for trace of A. Oops. Is equal to the sum over I of U sub I, okay, U sub I. And then what would you do? You would insert that identity somewhere.
My first guess would be to insert it twice, once in between bra and A, and once in between A and ket U I.
I think you need to do it only once.
Okay, then I would do it.
Let's try one. In any case, once is easier than twice.
For sure.
And so we should try once first, and if we end up being in pain, we can consider twice. Be lazy. Now you see that something that often is a difficulty is that here I wrote this with I, but here I'm already using I, right? So here I need to come up with another index name, right? So maybe I'm going to go I and J, and I'm going to keep I going with the UIs, and I'm going to use J for the V's. So I have UI, A, and maybe here I can insert the VJ. And then I have UI. And then what can we do then?
Would it make a difference if you insert it before or after your A operator?
I can do that if you want.
I'm just wondering. We don't have to. I'm just curious.
Okay, so I chose to do it there. If you want, next we can do it on the other side. It's not going to change anything.
Okay. Thanks.
So what is the next manipulation you would like to do? You need to wear your bras and kets goggles.
So I mean, the only thing I can see, and I don't know if this would be the right thing to do, but VJ times UI, that bracket at the end, that'll end up just being a number, so we can scoot that around to wherever we need to.
Exactly. So let's. But you're right. You're exactly right. So this is a number, a complex number, and this is a number. So we are stressed by commutators, right? We have realized that things don't commute anymore. But sometimes we should relax when we're dealing with numbers, right? We can still swap them. And so we can rewrite these as still the sum on ij. And then I'm going to write the second number first, which is VJUI, and then the first number next. And then, maybe tell me what happens next.
So now those two UIs are right next to each other in the exact structure of the identity operator.
Yes. So we use the closure relation in reverse, and we have the sum over J of VJ A VJ. And so we see that we started from the trace of A being expressed in terms of the matrix elements of A in the UI basis, and we end up with the same expression being equal in the V basis. So the trace does not depend on the basis you're choosing, and so indeed it's a property of the operator and not a property of the basis. One of you were asking if it would have changed anything to insert VJ here. Here, it's not working. Here instead of there, and you see that it would not, right? Just the only difference is that we would have had matrix element appear in second position instead of first position, but we would have done the same swapping to make appear the closure relation for the UIs. So this closure relation would have appeared here instead of here, but it would have been the same. But maybe you can do it for yourself to feel more confident about it. You feel good? What about the answer to the next one? What would you say for the next one?
Are we assuming that the basis that we're working with, that those are eigenstates of the operator A?
So the question does not assume anything, but you're right in saying that we could write the matrix that represents, we can write a matrix that represents operator A in a basis that is made of the eigenvectors of A. So then what would be the appearance of that matrix? So maybe I could do the drawing. If we were to construct a matrix that represents A in the basis
I think you froze.
Yeah.
Unless you just stop writing.
Okay, I'm sorry, I don't know what. Can you hear me now?
Yep.
Yeah.
Yeah, that's better.
Yes.
I'm not sure what happened. I think my my Zoom app just crashed. Broadcast. And so I'm not sure. Start to share. I don't know what it says. Okay, and maybe you were answering, but I was repeating my question without having any feedback. That's all right. So I forgot where we kind of dropped out. So what would be the representation of the matrix given the eigenvalues AI and the degeneracies of these eigenvalues GI?
So if we're in a basis where they're all eigenstates of A, then the operator matrix form would just be a diagonal matrix.
Right, so we have 0, 0. And we have stuff only on the diagonal here.
Yep. And those are all the eigenvalues on the diagonal.
Right. So that means that, for example, I would have A1, 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 etc. And I would have that G1 times. Right. And then I would go to A2, A2, G2 times. And so forth, right? And so if we wanted to write the trace of A, what would you write?
It would just be the product of GI and AI, the sum of the products of those.
Right. GI, AI, for I equals 1 to some number, which is not the, that number is not the order of the matrix, it's just the number of different eigenvalues. Okay, that's it.
Sorry, is it the number of eigenvalues or eigenstates when you have degenerate?
No, because so
values?
yeah, there is an eigenstate for each one, right? For each one. You remember we had this problem in which I forgot how it was presented, but you were asked to, we were considering a particle that could be in 3 different locations. Let's say 1, 2, and 3. And we would say that the particle is in state 1 when it is located on site 1, state 2 when it is located on site 2, state 3 when it is located on site 3. And then you were asked to write R plus, which was taking the particle from 1 to 2, from 2 to 3, or from 3 to 1. And you were also asked to write R minus, that was going the other way around. And then we defined, you remember, you see what I'm talking about, right? And then we wrote R plus plus R minus. And we looked for the eigenvalues and eigenstate. And in fact, I made a mistake because I had not realized when working out the problem with you that one of the eigenvalues was twofold degenerate. So I think that in this case, the values were, let's say, H1 equals -1, H2 equals -2, and H3 -1, sorry. I think that's what we found. Do you remember what I'm talking about? Oh, you have dropped again?
Yeah.
Oh no. Okay.
Yeah, no, I vaguely recall.
So these are the eigenvalues that we found for this operator. And so that means that, you know, since this is going on in a 3-dimensional space, right? You have 1, 2, 3 dimensions. That means that there is one direction that corresponds to H3, not bar, just H3. Right? And then you have 2 directions corresponding to H1 and H2. So just with the problem as it was set, there is no way to be constrained as to which direction is H1 and H2 pointing. So you need to make a choice. Right? So like, for example, this is one choice that I represented, but this choice would be equally valid, right? Now, so this is very mathematical. Now in physics, in order to make that choice, you choose something that you could measure. And so in the case of the angular momentum, we have seen that if you measure the magnitude of the angular momentum, you're going to find one of the eigenvalues of this quantity, which can be written in the form L plus 1 h bar square. Right? The state space of angular momentum it has an infinite number of dimensions, right? And there are sectors in that space corresponding to each possible value of L, where L is equal to 0, 1, 2, and so forth. Right? So if your measurement gives 0, then there is only one angular momentum state of, and I'm writing only the integers. I should write the half integers as well. But if your measurement gives 0, then there is only one angular momentum state that has a magnitude for the angular momentum that is 0. And then you're done, right? There is no further specifying the state. If, however, you find L equals 1/2, you know that there are two possible, there is a two-dimensional space, subspace that corresponds to that. If you find 1, there is a three-dimensional subspace corresponding to that. And so in order to identify directions in these subspaces, what you do, you say, okay, I'm going to measure something else. And the something else that is used generally is LZ. It's very silent. You're still with me, or am I by myself?
Yep, no, I'm following.
Okay, I'm sorry. I have a fear of abandonment. So you measure LZ, and then you know that the outcome of LZ is going to be something that goes from minus L plus 1 and so forth to L minus 1 or L, right? So you have 2L plus 1 possible outcome of the measurement of LZ, which corresponds to the fact that the subspace associated to each possible value of L is of dimension 2L plus 1. So in the case of this matrix, let's say that as I drew here, we have G1 that is equal to 3, and G2 maybe that is equal to 2, for example, and maybe G3 is equal to 1. Okay, so if I measure A and I find A3, then I know that the system that I measured is in the state corresponding to this eigenvalue, and there is only one such state. So that means that I have a one-dimensional state space, and I know which state space I am in, one dimension. So I'm done. If I find A2, since there are two eigenstates, there are two dimensions associated to A2. Another way of saying that A2 is twofold degenerate. That means that there is a two-dimensional state space associated with this value A2 outcome of the measurement of A. So if this was a physical problem and I wanted to specify the state more uniquely, then I would need to find something else to measure that would identify the eigenvector of that other thing that I am measuring that is in the plane corresponding to the eigenvalue A2 that I found in my first measurement. And the second measurement would specify the vector in that subspace corresponding to A2. And then, of course, in the case of A1, if I find A1, then I'm selecting a three-dimensional subspace to specify the state of the system, and I need to measure something else to identify in which direction in that space corresponds to the state of the system. Is that helping?
Yeah, no, I was just kind of making sure I was understanding
No,
what that
that's
n
good.
was, so that helps. Yeah.
Okay, that's good. That's good.
Professor, can I ask how do the subscript relate to the dimensions? Why is A1 third dimension? Why is A2 second dimension?
No, here it was just an example. Right? What we wrote here is very general. Here for the discussion, I just said, okay, let's say that G1 is 3, G2 is 2, G3 is 1.
Okay, so it's
just for the discussion. I wanted to put numbers, but in general, okay, let me remove these numbers. If the eigenvalue A1 is G1 degenerate, that means that when we measure A and we find A1, then that amounts to selecting a subspace of dimension G1 for the description of the state of the system.
And sorry.
No, go ahead.
How do we know how many dimensions we're talking about here?
So you see that here it's completely abstract and unspecific.
Okay.
Right? But an example that we have encountered already is the example of angular momentum. So if I were, maybe I can erase that. If I were to do the same thing for L, right? So you know that L can be represented by a matrix. And if I use eigenstates of L to represent L by a matrix, I'm going to have the first one is going to be 0 times 0 plus 2, so that's 0, right? That's the first eigenvalue. The second eigenvalue is going to be for L equals 1/2. Okay, so I have 1/2 times 3 halves. That's 3/4 of h bar squared. But you know, because we have studied angular momentum, you know that when a system is found to have this magnitude of its angular momentum, there are two states corresponding to that, right? So that means that L, so that value of L is twice, maybe I should have L square, is twice degenerate. So that means that this eigenvalue is going to appear twice. And the next one is going to be for L equals 1. So you see that 1 times 1 plus 1 is 2. So we have 2 h bar square. And you know that it's going to appear 3 times, right? And then that continues like that. And then we have all zeros here. So if you measure the magnitude of the angular momentum squared, and you find 0, then you see that there's only one direction in the state space that corresponds to 0. So you're done. You cannot specify the state of the system as far as angular momentum is concerned. You cannot specify that state more precisely. If you measure L square and you find 3/4 of h bar squared, you see that there are 2. And that corresponds to 2 dimensions.
Okay.
And then if, for example, you were asked to establish the state or prepare a particle in a state that is fully determined, then you will need to use some other quantity. And so what we have seen is that you could use Lz. And so if you measure the Lz value for a particle that you have found to be in that part of the state space of angular momentum, you can find either plus half h bar or minus half h bar. And then you can say, okay, could decide that this one corresponds to plus half h bar and this one to minus half h bar, and so forth, right? So for here, it's going to be the same. You can, if you find 2h bar square, then if you want to specify the state more, you can measure LZ, and you're going to find either minus, 0, or plus h bar. But at the same time, there was a choice that was made, right? You chose to measure LZ. You could also have measured LX, which would have been equally acceptable.
Okay, thank you so much.
So there is that amounts to choose. No, that's okay. That amounts to choosing a basis. So like we start talking about angular momentum. So you start choosing your coordinate system by saying, okay, I'm going to measure the magnitude square of the angular momentum. But each value of the angular momentum square does not correspond to a unique state. It corresponds to sub-state spaces. So each value of L squared sets up a vectorial space of its own. And then to be more accurate, you need to measure something else. And usually the choice that is made is to measure LZ. Is that helping?
Yeah, thank you so much for that explanation.
This is very important. This is very important. Okay, do you want to keep going? What do you want to do?
I had a question
to discuss.
Number 3. So it seemed pretty straightforward, apart from like, I just wasn't sure if we were assuming that the operator B on like parts, I think it's.
Okay, no, you have to slow down. 2, 3, like this one?
Yeah, so for part C and below, and like part C and D, like, are we assuming that those other B and C are also under the orthonormal basis given at the beginning?
Given. Okay, so that's exactly what I want to avoid. You see that you're told here about 2 operators, A and B. These operators, they exist independently from your choice of a basis. Then when calculating the trace of AB, maybe you may use a basis. But A, B, and the product AB and the product BA is something that exists independently from any choice that you make. Right? So this question, maybe to answer the question, you can decide, okay, I'm going to use a basis UI. But the question makes sense without any assumption about the existence of a basis also. You see what I mean?
Yeah, I understand. I was still just like trying to grapple with the idea of what a trace or tracer was. So I was referring back to the beginning of the question.
So you can use that. So here I'm explaining. I cease to explain what the trace is. When answering this question, it's probably a good idea to invoke a number of bases to figure out the answer.
Okay.
But the question does not lose its meaning without the existence of a basis.
Okay, so because what I was trying to do was the basis on A and B. So my question was, since both A and B are being traced, so in my mind that means like that the summed up diagonal portions of the matrix A, or the A is being multiplied by the summed up diagonal portions of matrix B. I was wondering if we should use the same basis if we use a basis, if we decide the basis at all.
Okay, maybe that. I'm not sure. No, Zola. I'm not sure. I'm not sure I understand your question. But you know you can use the definition that is given earlier and write trace of AB. So we have seen that trace of AB is a number that, of course, it depends on A, depends on B, but we have demonstrated earlier that it does not depend on the choice of the basis. Right? You agree with that?
Yes,
That was the first. That was the first question, right?
Mm-hmm.
No matter what is the basis, you find the same thing. So it's not a property of the basis; it's only a property of the operator from which you obtain the trace. Now, what you can do is say, okay, using a first basis, let's say UI, but you invoke that; it's not pre-existing in the problem.
Yeah.
But invoking that basis, you can write that the trace is UI AB UI.
Yeah, that's at first, and that's why I was wondering, like, if the UI, like when I invoke UI basis, like I don't know. I guess my question doesn't make sense that much, but I was just wondering separately, would that mean that the basis UI applies to both the operator A and the operator B simultaneously? Like,
but that's the thing that bothers me with your question. The A and B, they know nothing about any basis.
Okay, well, and
right. When we talked about rotations, I was taking the example. I don't know if you have one of these. The sound was weird. You're still with me?
Yes.
Okay. We are talking about rotations. You can rotate, and if you have one of these chairs, that can spin around, you can rotate in your chair without wondering about any metrics that describe the rotation.
Okay.
And if you want to describe the rotation using a specific coordinate system, then you have a matrix that represents that rotation. But the rotation, the planets, for example, they spin without matrices being involved. They just spin. It's not right. There's not even a coordinate system. That things are still spinning.
Yeah, I think I understand. I think I was just trying to go about it by replicating part A of this question, but
that's correct. That's you can use to calculate the basis, the trace. You're going to use the basis, but the basis is just a tool. It's not. It has nothing fundamental to it.
Okay. Yeah, and
So shall we solve this one? How do you deal with that?
Well, I had written down like how it was written down on part A, and so what you had written down right now is what I have so far. So I was still going to try figuring it out on my own.
Okay, so the thing, you always use the closure relation for all these deals, right? So you do that, UI, okay, and then I'm going to bring in UK, B, UI. Okay, so here I have not done anything, but again, as one of you pointed out earlier, this is a number, and this is another number, and the product of numbers is commutative. So I can rewrite this in the same way, but the two numbers swapped. So I have UK, B, UI, UI, A, UK. Oops. Come back then. UK. And then again, you say, okay, we are summing over I, and we have this UI, that's the closure relation, so that's the identity. So this is equal to the sum over K of UK, B, A, UK, which is just the trace of BA. Okay.
Yeah, that makes sense. Thank you.
Okay. So the next one is the same with but with 3. So I'm not here. Sorry. The next one is the same with 3 operators. I let you do this one. I think if you understand this one, you should have no difficulty doing the next one. Just you need to invoke the closure relation twice instead of once.
Yeah. Awesome. Thank you for explaining. Yeah, I think I with the like how I would apply my basis on there, but you explained it that it doesn't really like the operators are independent of those. So I think that makes sense for me. Thank you.
Okay. This problem 4 is essentially done in the. We went over it in class together on Monday, I think. And it's in the notes, so it's just for you to follow the notes. Okay. That was the quiz essentially, and the difference in the quiz was that I had written the basis with this state here and this state there, right? So that was just changing the order of things, but other than that, so be careful. Don't rewrite the solution of the quiz. You have to pay attention to the order of the unit vectors. Do you feel good about the other problems, or what? Or is there any one of them that you would? I'm by myself again.
No, we're here.
Oh, okay.
Yeah.
Sorry. So I was asking, is there a problem you would like us to look at together, or do you think we are done?
I had a question, not with homework 3, but in homework 2, the one we just recently submitted. There's a couple where we had to use the S matrix, and I could have sworn I copied the S matrix directly from the Townsend first edition textbook, but I think when mine was graded, Philip mentioned that it was inverted or something. And I just wanted to get a clarification on what that actually was, because I'm a little confused on like whether what you're converting or what you're converting into, I guess, if for lack of words, is put on the right on the ket, or
that was with problem 6 with the X and Y polarization of the photon and the L and R polarization.
Yes, yeah. I was just a little confused because I looked at the Townsend textbook directly, and I think it was like pages 80 through like 82 or something. And I copied.
So is the question about the grading of your paper, or?
Just wondering what S is. How do we create S? And like if we could write out that matrix and know the basis that we're going to and from and how to build it, because we're pretty confused about it.
Oh, okay. Okay. So yeah, on page. So if all right, and I should post the solution actually for that homework. I forgot to do that. So I do that after class. But essentially, we have the left circular polarization that is equal to 1 over square root of 2 x minus I y. While the right circular polarization is 1, and that I think that's oh no, that was not given in the question. You just had to go back to the notes or to the book. X plus I. Okay, and then you were asked determine the S matrix that can be used to transform a column vector representation of a photon in the polarization X, Y to the same photon, but in the L, R basis. And so the way to do this is to write a matrix that is the following. So it's just X, L, X, R. And again, I'm starting here with L because in the question, you have the question under your eyes, right? L is listed first in the basis, and R is listed second, right? So that's why I'm using that order. And in the same way, here I'm using X first because X is listed first, and I use Y next. And so then if you were to multiply, let me copy it. We use that matrix to multiply a state that we have in the LR representation. So let's say that state is psi. So it just gives
Before we go any further, I was in, and this is where my confusion is coming from, is in the book, there's a paragraph and it reads that we create S matrices by taking the inner product of the basis ket of the representation we are transforming from with bras of the representation we are transforming to. And that sentence to me says that we should have kets in the X and Y and the bras in the L and R. And that's where my confusion is coming from.
Right. Yeah. So what you're saying, okay, let me read the question. Determine a 2x2 matrix that can be used to transform the column vector representation. Oh yeah, so we want to go from XY to LR. Well, here I'm doing the reverse, right? So that means that then the matrix that goes the other way is going to be S DAG.
Wait, so then is the first one that you wrote, is that Y? Does that take us from L?
Yes, so let's do it. Let's do it because I think it's nice to see. So let's do it. Let's write that product. And you're going to see that it takes us. You see that I start from a LR representation. And so if this is correct, that's going to take us to the XY representation, which is the question was written in the reversed way. But at the same time, what is the actual? Verify that S is unitary. Right. Okay. So maybe I wrote it reverse to what is asked for S. Let's do the product. So it's XL times L psi. XL times L psi plus XR times R psi. And down here, we're going to have, sorry, L psi plus Y R psi. Right? And again, you see that you can use the fact that L plus R is 1. And you see that this ends up being X psi Y psi, by which we verify that this matrix that I wrote here, takes us from the LR representation to the XY representation. And I realize now that the question was asked the other way around. So we are asked to write S to take from XY to LR, and I wrote the reverse.
Okay, so if we got marked off points because he said that we did the reverse matrix when actually we did the correct matrix, should we talk to Philip or should we talk to you at some point?
To Philip. You talk to Philip.
Okay.
So no, but maybe you. I was answering wrong right here. So maybe you did it right. So if you did it right, you should not have lost points. Maybe it was because that's what I wrote in my solution. So maybe it was going off my solution.
Okay. Yeah, I'll schedule some time to talk to him.
I write to him. It's possible that I poorly influenced him with the solution that I gave to him. I made the mistake myself when writing the solution. I was not paying attention.
Awesome. Yeah, thanks for taking some time to talk about it.
Yeah.
Okay. I will write to Philip so that he can adjust accordingly. But what is important is that you see how that works. Okay. Any other question you want to discuss? I take that as a no. I don't even know how many people are still around. Oh, still 26. Okay. Any other points you would like to discuss?
If we could actually go over number, I believe it's number 7A.
Five. Uh-huh.
I'm just
okay.
I'm unsure on the probability computation.
Okay. So what would you be tempted to do?
Well, my first thought would be to try and get the expectation value for JZ, but that looks like that's what part B was. And so I guess.
So no. So let's start. Let's start by writing psi. Okay, so let's write psi information that we are given. And so let's write psi in terms of these kits. What would you write?
Would it be 1
you see the
first ket plus 2 times the second plus
okay, yeah, let's okay. Yep, I think you're right. So let's factor out maybe the 1 over square root of 14, so that way I don't write it too many times. And then I have 1 times 1, 1. Then I have 2 times 1, 0. And then I have 3i times 1, -1. Okay. And we are going to measure on this state. And you see that this corresponds to the outcome of the measurement being +1. This corresponds to the outcome of the measurement being 0. And this corresponds to the outcome of the measurement being -1. Or minus h bar, I should say. So what is Born's postulate telling you? If I call the probability, let's call them P of plus h bar. So the chance probability of obtaining h bar is going to be 1, 1. So that's the bra corresponding to the ket, that is the state in which Lz is plus h bar. That multiplies psi, magnitude squared. So in this case, this inner product is just going to give us 1 over square root of 14. And then when you take the square, it's just 1 over 14. Then that's good.
Yeah, that makes a lot of sense. Thanks. I just have a lot of.
Oh, yeah, you're here. Okay, you're here.
I need a lot more practice on going from these the kets and matrices.
So always when you want to figure out that you are talking about measuring A for a state psi. To calculate the chance probabilities of obtaining each possible value, so each possible eigenvalue of A, you need to take the component of psi along the eigenvector corresponding to the eigenvalue of A that you're considering, and take the magnitude square.
Awesome. Thank you so much.
Then if the eigenvalue is degenerate, then of course your total probability will be the sum of the probabilities for each dimension in the degeneracy. Right? So that means that it will be the sum of the squares of the amplitudes. But we're probably not going to have degeneracies soon. Okay. Are there any more questions in this problem that?
Professor, can you give us a little hint about problem 5b?
5b. Oh, 5b. Yeah. Oh, B. I was not reading. I was reading A. With omission under. Oh. Well, tell me what stops you from answering this question.
So I'm understanding what it's asking for, but I'm a little confused how to start.
So for this to be correct, for alpha A to be Hermitian, you need to have alpha A Hermitian conjugate equal alpha A, right?
Yep.
Now, how do you evaluate this?
So it should be complex conjugate of alpha multiplied by alpha transpose and complex conjugate both. Yeah.
So transpose and complex conjugate, that makes sense only if you're dealing with a specific matrix representation.
Mm-hmm.
Well, here we just have the operator, right?
Yep.
So you need to have
Alpha star. So
if this is true, then this is true.
Mm-hmm.
But then you are told that A is Hermitian. So that means that A dag can be replaced by A. So you have alpha star A equals alpha A, which means that alpha star must be equal to alpha, which is just saying that alpha is real.
I see. Yeah, that makes sense now. Thank you.
You're welcome. Okay, I have the impression we're running out of steam. Should we call it a day? Or are there any more questions?
I don't have any more.
Okay, let's call it a day. I'm happy to stay online if some people want to discuss anything. I will post the I forgot to do that today. I will post the solution for homework 2. I apologize for not doing that earlier. I don't know what I was thinking. You should don't hesitate when I forget. I'm as you might be perceiving already, I am extremely forgetful and easily distracted. So when you see that I'm forgetting something like that, please remind me and I'll do it right away. And then on Monday, we will move to a different topic with time evolution of quantum states. So that's when we are going to start talking about the Schrödinger equation. And so these spin 1/2 particles that we have been discussing in a relatively abstract way until now, we're going to place them in a magnetic field in such a way that the magnetic moment that is associated with the spin is going to interact with this magnetic field. And we're going to see how the precession of spin 1/2 particles is described quantum mechanically in a magnetic field. The big application of that is nuclear magnetic resonance that is used, for example, in medical imaging. So we'll start talking about that on Monday. Have a good weekend, and I can stay while people disappear if you want to stay to talk about it.
Thank you, Professor.
See you. Have a good weekend.
Thank you.
Thank you.
You're welcome. You're welcome.